questions? Good morning. All right, so let's wrap up ODP 209. So 209 was a function that removes the second node of a linked list. And I set it up like this, right? So you receive a pointer to the first node, I called that n. I set temp equal to the next node, and then I said n next equals temp next, and then freed temp. Now you didn't have to free the node in this case, but let's take a look at this. So this is edit n. So I said temp equals n next. N next equals temp next. And then free temp. Alright, so what's going on here? We're past a node to n, a pointer to n. And we want to get rid of this. So we could simply do n next equals n next next. That would do the same thing as these two statements, right? Since temp is n next, temp arrow next is really n arrow next arrow next. So I could do n next equals n next next, and that would adjust this pointer. But if I do that, I have no way to free this node because I lost my only reference to it. If I say free n next, I'm going to free this node. And that's not what I want. So I could use a temporary node to remember what n next is equal to, and then free that afterwards, which was what I did. And I did temp next just to make my life easier. And you might think, okay, well, I'm just going to free that node first before I lose the pointer. And then I'm going to set n next equal to n next next. But I'm probably going to get an error at this point, because once I free n next, I'm not allowed to use anything from that node. And this reference to n next is bogus now. And when I try to get this, I'm not necessarily going to get the same value that was in here. And so this is going to end up pointing, you know, somewhere bizarre. So a lot of times when you're deleting, you kind of have to use temporaries. But I like using temporaries anyway. Even if you could write your code without it, go ahead and, you know, give these things names. Set temp equal to n next. And, you know, maybe go ahead and set, you know, last equals temp next. And now, what do I want? I want n next to point to last. That's just n next equals last. And now I want a free temp. I'll just free temp. And you almost don't have to think about it. You have to think about setting these things up. But then if you know what you want to have happen, you know, each action corresponds to a line of code that really just kind of says, have n's next field point to the last node. Get rid of the memory being used by the temp node. So never hesitate to use temporary variables. Unless you've got a teacher who says, don't use any unnecessary variables, and then you gotta, like, you know, put things together and be slick about it. but I think it's nice to use temporary variables. All right, so any questions on that ODP? All right, and I see lots of 20s out of 20s, which is awesome. So I'll push those grades out. Cool. Let's see, in my last one, why don't I have to free last as well? Excellent question. So if I do this, if I said last equal to temp next, and then end next equals last, so last is this node over here. I don't want to release that node's memory, right, from the system because I have data stored in there. I have a struct node star that's pointing to it, but last is a local variable, right? Last would be something that, you know, I declared inside my edit function, and I set it equal to the address of last. Declaring a variable is different from calling malloc. Setting a pointer equal to something is different from calling malloc. The only time we need to free is when we've done malloc and we want to release that memory that was allocated. So I need to free temp for sure, but that's the only thing I've got to free. And yeah, you definitely need a delete all function that you're going to call after the user says X to say, hey, release all the memory that's still being used in the list. Because when you delete a node, yeah, just free the memory right then. But when you're done, you might have a list with 5 things in it. You've got to free all 5 of those things plus the Sentinel node storage. So make a separate function for doing that. And that's that release all nodes or free willy function or whatever you want to call it. If you are in a while loop until current equals null, then just put a break and you will break from the loop and there will be no problem. Well, it's possible that that's true. It's possible that it's not true. It's not the fact that you have a while loop or that you're breaking when current is null. It really depends on what else you're doing in there. But there's nothing inherently, you know, wrong or dangerous about doing what you've just described. You can do a while forever loop and break out when current is null. You can do a while current is not null. You can do both together. And yeah, as long as it makes sense to you and it looks like it works and you've tested it thoroughly, you're probably good. But definitely try to make sure that whatever you're writing makes sense and it's not just, you know, keep changing it until it doesn't segfault and then call it good. Make sure it's reasonable. I got a segfault after using the free all function. It also freed all the memory for valgrind. The free all function can be tricky because we're freeing nodes that we're also using to move down the list. But remember, think of your list as collection of linked together things, and starting with the Sentinel. Well, we can't free the Sentinel until we use it, so next equals Sentinel next, free the Sentinel, and then, or current. So save the address of the next node, and then free the current node, and then set your current equal to that next node that you saved. And once you free current, you can't say current equals current arrow next. And that's a possible source of seg faults. So don't do this. Right, if that's the effect that you want, save current next somewhere, free current, and then set current equal to that value you saved. Alright, so don't ever use the thing that you just freed. Alright, and I've started getting email requests from people asking if I can download their repositories. I will let you know Friday morning after 8 if there's a problem. If you want me to check your repository ahead of time, you have to do that within 24 hours after I post the assignment. So that would have been last Friday, but I'm not going to do those checks after that. So make sure that, you know, it's named linked list 1 uppercase, linked list 2 with uppercase L's. Make sure I'm listed as a reporter, and you should be good. All right, other questions? Alright, so let's look at stack implementations using an array. And we already looked at implementing a stack using a linked list, and the setup was pretty straightforward. We would push into the stack by inserting right after the sentinel. So we'd add a node to the beginning of the list. And when we wanted to pop a node from the stack, we would just take the node at the beginning of the list and return that, and then delete it from the list. And that works well with a list because, you know, remember lists, we can put things anywhere that we want. We could have added, you know, pushed at the end and popped from the end, but we'd have to move all the way down through the list to get to the end. But with an array, we can't easily insert something at element 0 because that requires us to move everything down in memory. Right? That was the whole reason we got away from arrays. On the other hand, with arrays, we can always add something to the end, and that's very efficient. If we have a variable that tells us where the last element in the array is, and we want to add one more element, just bump up the value of that variable, store your element there. So that's how we're going to implement a stack. So let's picture an array. And let's just suppose it's an array of 10 integers, or whatevers. And let's suppose the array is actually called stack. So what are the two main operations we do with stacks? Push and pop, good. So let's push a number n onto the stack. And we've got to store it somewhere in this array. Where should we store it? Well, let's make a variable that's going to record the location where we're going to store the next thing that we push. So we're going to call this SP. That's short for stack pointer. And to push something, we're just going to say stack bracket SP equals n. So if I say push a 5, that's going to take a 5 and store it at location 0. And then when we're done, we have to increment SP so that the next time we push, it doesn't overwrite the 5, it goes into the next location. So we'll say SP equals SP plus 1. And while we're at it, let's talk about our initialize function. To initialize the stack, we just set our stack pointer to 0. So stack pointer is right here. We push a 5, it writes a 5 at that location, and then increments the stack pointer. Push a 10, save a 10 at the location given by the stack pointer, increment the stack pointer. We'll push one more. We'll push a -2, save it at the location given by the stack pointer, increment the stack pointer. This is order 1. If we're at the beginning of the stack, if we're way down at the end of the stack, it's just 2 operations to push something. But it's a little different from our sort of physical model of a stack. With a physical model of the stack, right, we pushed a 5, and then when we wanted to push a 10, everything would kind of move down and the 10 would go on top of it. And so we'd have a 10 and a 5, and then when we wanted to add something else, those would move down and we put the new thing on top of that. So in the stack of dishes, right at the Chinese buffet, the whole collection of data is moving every time that we push or pop. That's inefficient, right? So instead, we store these things in different locations, but we have a notion of where the top of the stack is. And the top of the stack is like the action end of this structure. It's the point into which you're going to push, the point from which you're going to pop. And top of stack for us is really just the stack pointer. So we're not going to make that a separate thing. Alright, so how do we pop? Someone says, hey, I want to pop some data. What are our 2 instructions? Yeah, so return something and do SP equals SP minus 1. Well, what's the value that we want to return? How do we find that value in our stack? SP minus 1, stack bracket SP minus 1. Right, here's our stack pointer right now, so the value we want to pop is 1 spot before that. So let me just do it like this. Let's decrement the stack pointer first, and then return stack bracket SP. So we say pop, what do? Decrement the stack pointer. And then return the value at the stack pointer, so that's going to give us a -2. If we pop again, our pop function says decrement the stack pointer. And then return the value at the stack at that location. Well, that's the number 10. So the last thing we pushed was a -2, that's what we popped. The thing we pushed before that was a 10, that's what we popped. If we were to pop again, we would return the 5. And again, notice, even though we popped off -2 and 10, they're still sitting in the stack. And yeah, you could do that in one line. We could return stack bracket ---- SP. Absolutely right. We'll write that out in a minute. Alright, so popping does not actually remove your things from memory or from the stack. All it really does is adjust the stack pointer. So now if I say let's push a 16, it says store 16 at the location given by the stack pointer. Well, now we're going to store the 16 right here, and then we're going to increment the stack pointer. So popping doesn't actually get rid of that 10, but it moves the stack pointer so that location is no longer considered part of the stack, so that the next time we push, that 10 gets overwritten. So we're not wasting the memory, even though the values that we popped off are still in memory. Those spots are available to be reused. Alright, and if we want, we could do this more succinctly. Our push is simply stack bracket SP++ equals N. And our return is return stack --SP. So our push uses a post increment, our pop uses a pre-decrement. Those are going to travel in pairs. Post inc, pre-dec. And in this interpretation, what is the stack pointer? Stack pointer is where the next push will be saved. So this is why we initialize the stack pointer to 0. That's telling us the next time we push, it's going to stay at location 0. So when we see the stack pointer is right here, that means this is where the next value is going to be pushed. So the last value that was pushed, the value that's actually on the top of the stack, is always one spot before the current stack pointer. Which is why when we want to pop, first we have to decrement the stack pointer and then return that value. Alright, and let's look at our error conditions. So when is the stack full? What one line of C code would tell me that the stack was full? Assuming in this case our array is size 10. Today is all about edge cases. So someone said if stack edge equals null, that's probably the right spirit of it. But yeah, let's be more specific. If the stack pointer is equal to 10, that tells us the stack is full. Because that would be trying to you know, if we tried to push one more thing, it would be trying to store it at element 10, which doesn't exist. The problem with using null is there is actually something at element 10. It's a valid location in memory. It's most likely accessible. There's nothing about that that'll tell us this is not part of the array. This is beyond the end of the array. So we have to know what the size of the array is, how much space was allocated for this array called stack, and then check to see if our stack pointer is going to go beyond that. So when we push, we could check to see if the function is full, if the stack is full, by seeing if the stack pointer is 10. So what's the empty condition? How do we know the stack's totally empty? So it's probably 1 or 0 or minus 1. Right? It's always one of those for these kinds of questions. If the stack pointer is 1, the stack pointer is where the next push will be saved. Stack pointer 1 means the next thing we push is going to go here, which means there's still one thing back here. So it's not quite empty yet. But if the stack pointer is 0, that means the next thing that we push is going to go right here, which means there's nothing in here stack-wise to begin with. That's when our stack is completely empty. And you can kind of check these conditions to see if these would cause an error. If our stack is full, a push should cause an error. Well, if SP is 10 and we push, we're going to try to save n at element 10 of our array, and that doesn't exist. If our stack is empty, a pop should give an error. Well, if SP is 0 and we try to pop, we're going to subtract 1, which will make SP minus 1, and we'll try to read element minus 1, and that's an error condition also. So for this implementation, there's your edge conditions. And so, you know, before we push, we'd want to check to see if the stack was full. Before we pop, we'd want to check to see if the stack was empty. All right, let me show you an alternative way to do this. And still, the first thing we push is going to go here, the second thing will go here, the last thing before we're full is going to go there. But here's a totally different approach. Suppose that when we want to push something, first we increment the stack pointer and then we save in that location. And when we pop, first we return the value that's at the position given by SP, and then we decrement. And to initialize, we start the stack pointer at -1. So the behavior is the same. When we say push, stack pointer is -1, it'll increment to a 0, which we'll put it right here, and we'll save our value at that stack pointer location. When we say push again, we'll increment the stack pointer. So stack pointer will be here, and we'll save at that location. When we pop, we'll return the value from this location and then decrement stack pointer. So this would be stack bracket plus plus SP equals n. We do a pre-increment, and this would be return stack bracket SP minus minus. We do a post decrement. And in this, SP is where the next pop will come from. So this was post increment for push. This is a pre-increment for push. This was a pre-decrement for pop. This is a post-decrement for pop. Here the stack pointer is where the next push will be saved. Here the stack pointer is where the next pop will come from. Here we initialize to 0. Here we initialize to -1. So when is the stack full? SP tells us where the next pop will come from. So if SP is equal to 9 and we try to push, first thing we're going to do is increment to a 10 and then try to save at location 10, and that's going to be where we run out of space. So it's full when SP equals 9. On the other side, we're popping, we're popping, we're popping. If SP is equal to 0, a pop will return the value at this first cell. That's not an error condition yet. It'll return the value here and then decrement stack pointer to -1, which was our initialized condition. That's when we know the stack is empty. So here the stack pointer is 9 for full, -1 for empty. Here it was 10 for full, 0 for empty. Okay, there's harmony between these different approaches. I don't want you to memorize these. If you're trying to implement a stack and you're going to use post increment for push and pre-decrement for pop, don't try to remember which way it's supposed to be. Don't go back to your notes to look it up. Figure it out, right? This is how you're going to internalize what a stack is and how a stack is implemented with an array. Figure these things out. Now for a test, put it on your note sheet if you want, but before you get to the test, hopefully you've done enough stacks on paper and in code and figured it out each time that you can, pretty much crank these out without a whole lot of weeping and gnashing of teeth. But the first few times, just think about it, draw some pictures, figure out, should this be, plus plus SP or SP plus plus? Should this be 9 or 10? Should this be -1 or 0? We can do two other variations. We could simply start our stack with this being the first location that we use, and we could grow the stack in this direction to the left. So we might initialize SP to 9, and our push would say use stack bracket SP minus minus, and a pop would be stack bracket plus plus SP. So there's at least 4 different ways we can implement a stack with an array. We usually do one of these two where we start from the 0 and grow to higher indexes. Alright, so pretty straightforward, but a lot of potential confusion as to, pre or post, increment or decrement, 0, 1, -1, 9, 10, 11. All right, questions about that? All right, let's go on to queues. So with a linked list, queues were a minor variation on a stack. Stack we inserted at the beginning of the list, we removed by taking off from the beginning of the list. And then with a queue, we inserted at one end of the list and we simply removed from the other end. And that works great with a linked list because we can put things in or take things out from anywhere in the list, and it's still very efficient. With an array, we don't have that efficiency. Remember, the whole issue with arrays that led us to linked lists was that if you want to insert something in the beginning, you have to move everything down to make space. So for the stack, we deal with that by leaving the data in its current location and just moving this pointer. We're going to do the same thing with a queue. But because there's two ends to a queue that we care about, we're going to need two pointers. So here's our queue. Here's some elements. And remember our two operations. We have an insert and we have a remove. So we insert at the tail and we remove from the head. So I'm going to have a pair of pointers. I'm going to call them T and H. And T is going to show me where I'm going to insert my next value, and H is going to show me where I'm going to remove my next value from. So I'm going to initialize my array by just setting tail and head equal to 0. And here's the idea. When I want to insert something, I'll put it right here, and I'll move the tail over to here. So let's insert a 5. Let's insert a 7. Let's insert a 9. Let's remove. Let's remove. And let's insert a 6. Okay, let's look at the picture first. So I'm going to insert a 5. That's going to go right there where the tail is. I'm going to move the tail. I'm going to insert a 7. Going to put it where the tail is. Move the tail marker. I'm going to insert a 9. Put it where the tail is. Move the tail marker. I have 3 things in my queue right now. I have a 5, a 7, and a 9. What order did I put them in? It's always left to right. 5, 7, 9. What's the first thing in my queue? That's what the head tells me. So when I say remove, I'm just going to read off the value that's at the head. I'm going to read off a 5. And then I'm going to move the head. So the head node goes down to here. I want to remove another value. I'm going to look at the head. That's the next value to remove. That's where we remove from. That's going to give me a 7. And I'm going to move the head. Alright, what's our queue look like right now? It has one thing left in it. That's a 5. We know, sorry, that's a 9. It's the last thing that we inserted. We know that 9 is the next thing to remove because that's what's sitting there at the head. And if we're going to add one more thing, we're going to put it right here at the tail. So this is, you know, a line of customers, and instead of the people in the line moving up, the cashier moves down the line, right? So they take care of this customer, and then they move here, take care of this customer, move here, and take care of this customer. If they finish with this customer and they move here, the line is empty. But if more customers come in, then the tail is going to move. And after they finish with this customer, they'll move here and deal with them, move here and deal with them, move here, and the queue is empty. All right, makes sense so far? So what happens when we add a few more customers? Let's say we've dealt with customer 9, and so we're about to deal with this customer, but we've got more customers that have queued up. We've got more entries in the queue. The tail is sitting right here. And we insert one more thing, and that thing goes right here. Where should the tail change to? The tail would need to wrap back around to the 0, exactly. The queue's not full, right? There's nobody sitting in spots 0, 1, and 2, so we're going to take the tail and we're going to wrap it around back to the beginning. And if another customer comes along, we'll put that value right here, and we'll bump up the tail again. And so right now, our queue looks like this. It starts here. It has all of these pieces in it, and it's also got this piece. So it's wrapped around. And if somebody else comes along, we might put them right here and move the tail to here. And now as we start removing, we'll remove this one and move the head to here and here and here and here and here, and eventually the head is down here. And if we remove that element from the queue, again, the head should wrap around. And now, you know, if this was our tail, we've got two things in the queue. 1, 2. If we add a third thing, it's going to go here. So this is a circular queue. And the image you can think of for this is an array that eats its own tail. So that effectively, if you go one beyond this, you're just back at the beginning. Alright, so when is a queue empty? It's empty when the head and tail are equal to each other. And so to initialize this, we just set head and tail equal to 0. And that tells us we're empty. Fullness is a little different. To tell if a queue is full, well, when it's actually full, when we've completely wrapped it, you know, filled up every single cell in here, we're going to find that tail and head are equal to each other. But that's the same condition for when the queue is empty. So we're going to actually say that the queue is full one spot before it's full. And we're going to say it's full if inserting one more thing would make it completely full. So if tail plus 1 is equal to head. Alright, so let's just, in our last 2 minutes, let's do some code. So insert n. Well, we insert at the tail, so q bracket t equals n, t equals t plus 1, and then we want to roll over if we go past the n, so t will be t plus 1 modulo 10 in this case, or whatever the size of your q is. To remove, we return the value at q bracket head, increment the head, roll it over at the end, and return that value that we found in the array. Is empty. Just return whether the head and tail are equal to each other. Is full. We want to know if doing an insert would cause the q to look empty. In other words, if adding 1 to t will make it equal to the head. So we can return whether the head is equal to tail plus 1 modulo 10. And init, just set everything to 0. And one more nod to abstract data types, right? Your main program that you write to use a queue would call init, is full, is empty, insert, remove. It doesn't care about these details. It doesn't know if inserting is putting a new node at the beginning of a linked list, or storing in an array and incrementing a variable and rolling it over mod 10, right? We don't want our main program to have to know that. It simply knows when I want to add something to the queue, I call insert. When I want to remove from the queue, I call remove, and so on. And it's modulo 10 because I made my array 10 elements long. So if t equals 9, then when I increment, it's going to be equal to 10, but I really wanted to go back to 0. So doing a modulo 10 will cause that rollover to happen. But more generally, that's the size of the array. Alright, that's stack and queue implementations. So think about that. Bring questions to class tomorrow. Finish PA2, get that turned in. Make sure I'm a reporter. Make sure it's named correctly. And I will see you tomorrow. We'll probably start talking about hash functions tomorrow. Alright, have a good afternoon. See you next time.